Okay, so we'll do some define a process first, which is very interesting, and then we'll do some computations and eventually come back to where we were last year. We'll define you've seen Poisson process. We'll define Poisson process. Definition is simple. So think of RD for the moment. You can do all of this over RD. And let's say A and B are compact sets of. You understand what compact? Closed and bounded. Yes. Compact subsets. And let's denote the area by the level measure in new way and area on. If you don't know what that is, all right. Then for homogeneous, I will tell you what homogeneous. Poisson point process. So from this class and onwards, I'll most likely say this PPT. With density lambda is a random point process. Part 2 with for the distribution probability number of points in A to be equal to K. So this is the count of the number of points falling in this set A, and the probability that that is equal to K is nothing but the usual Poisson distribution, that is lambda times nu A whole to the power K 4K factorial e to the minus lambda. So everything really has been scaled by this quantity lambda times nu over A. Physically, what is going on is that if you have a two, you get any set A over here. The density is nothing but what we really mean by density. That we expect the expected number of points find here is nothing but so expected number of points of A, which is the area of A. That's what the lambda means. So if I tell you the density of points in a certain area is lambda, that essentially means that if I multiply the area, that will give you the total number of points. So in here, everything is random. So the expected number of points in A is nothing but lambda times mu. This is saying it's also that the number of points falling here is also Poisson distributed with that mean. That's all it's in addition saying. You can define any, so you can replace first P with a Poisson to any other counting measure. The second and the third is just the point process. So it could be any point process over that.
Why is this called a process?
It's a point process. There's no reason to question why it is called. I could have called it point something.
Like, are those sets taken randomly or?
Yes, I'm not taking, no, I'm not defining anything over here. I'm defining this process over all of R2. You take any A, which is a subset or a compact subset of R2. This should satisfy this. That's A and B have nothing to do with randomness. Randomness is in the location of these points. That's what it really means. And why I have to take B is for extra property that if A intersection B is empty, that is their disjoint, then the probability of number of points, what did I this? Essentially independent. Both these properties completely defined by column pointers. Each subset, the number of points distributed is polygon, and two disjoint subsets, the number of points pointed there are independent. That is all there is to it. So that completely defines it. If you go back to the picture. So suppose I look at this side as A prime. What is the probability in particular that no point falls in A prime? That is essentially A equal to 0. That is just 1 divided by 1 is e to the minus mu. So this is also called a void probability. What is the probability that there is a hole in this? Goes by many names. You can call it a void or hole. These are used, the void probability is used. Essentially, it also will control the distance between nearest neighbors. Right. You see that why? So on this process, now I can start defining the distance between nodes. What is this process? It is just some locations. Now, if I look at this particular node and start asking you what is the nearest neighbor, what will that be? So if you know the void probability, I claim that you should be able to tell me something about the nearest neighbor distributions. So what is the definition of nearest neighbor? If there is nobody nearer than that. Yes. So what does that mean? What does that translate in terms of void probability? This particular node, if this guy happens to be the nearest neighbor, what geometrically has to happen?
If we consider a set having radius less than that distance.
Just the circle around here. If that has the radius, what has to happen?
Void probability will not be equals to 0 because
No, not 0. I'm not saying. So what is the event which makes this node the nearest neighbor? Is the fact that there is nobody in here.
yes.
So that means that this probability of this being R is the same as the probability of void probability of this set, which you can call it as a ball of X. These are intimately connected problems. The void probability, which is, I put a 0 over here, is intimately connected to the distances in this point process. You can do it slightly more formally. Pranchu, any questions?
No.
Okay. So any other interesting property which is obvious here at this time? This word homogeneous, that should also strike you. So homogeneous is nothing but because I'm saying the density is lambda throughout. If I make lambda a function of a location, that at point x the density is lambda x, then it's called a heterogeneous column quantity. We won't deal with this in those, but they're also useful too. So I'm just defining a new quantity. This is the definition, pretty much. So over R2, you look at any two subsets A and B. The number of points falling there are independent, and in each A, the distribution is the number of, so this is nothing but the number of points falling in region A. And mu A is nothing but the area of that region. So it's a Poisson distributed with lambda times mu of A. So in essence, the expected number of points falling in a region is equal to lambda times the area of that region. This defines my completely a homogeneous Poisson point process. Human density dependent on the location, then it's a homogeneous process. You know what it is. No. And when I say void is nothing but when I look at A equal to 0. The fact that a region doesn't have any points. And that is related to the nearest neighbor distance in the sense that if I'm looking at this point and this guy is the nearest neighbor, necessarily there should be nobody in this. So that is nothing but the void probability. That the number of points falling in this region except this point is 0. So now it becomes tricky. So last time we were doing this percolation over discrete. We knew where all these nodes were. Here, because it's a random process, the locations are not fixed. So if you're going to ask for saying the fact that what is the connected component of anything, I'm not even defined what connection even means. Soon enough, we are going to define a graph over this process. But then I have to worry about the fact that a node exists at a particular location. Because that happens with probability 0 here. What is the probability that a particular location X belongs to this process? Let's call this process P. What is the probability? X is nothing but a location in R2 belongs to P. X is a singular point. Why are you hesitating? This is in fact real. Particular location happens to have a point landing on it. Sorry. So what is my phi? Phi is nothing but over R2 from points. Collection of points. Now I'm saying I fix a location X ahead of time. What is the probability that one of these points lands up at X itself? Sorry?
1 by cardinality of R square.
What is cardinality of R square?
It can be any point, right? So.
No, what is cardinality of R square?
Not finite, right? That's why, like, it
That's
was
not the answer to this. It is 0, yes. But that is
otherwise, how can we say that? Like, it's very small, but why is it there?
think of a uniform random variable over 0, 1. Okay.
Yes.
What is the probability that U is exactly equal to 0.5?
0.
Why is it 0? The cardinality of this.
At a particular point, we cannot say it's a continuous.
I'm just giving you the flip argument. What you said was look at the cardinality of the whole set, divide it, and that is 0, so you're done. But this clearly is not, cardinality is not infinity. So then your answer should be just 1 by 1. Now you're saying something else. This is not any different than that. It's a continuous space. I'm talking about discrete points. It better be that. It's just a fact of dense versus not dense. The real line is dense, but I'm only doing discretely many points.
You're randomly choosing points on R2. So if lambda X is heterogeneous, then at some locations I can have more power.
Yeah, but still, this is still 0.
Yeah.
The probability is still 0. So that's why conditioning has to be very careful, because I will start talking about a connected component of X, and for that I'll have to worry about this. And this is the reason I have to be careful. If this was not 0, then I would happily taken condition probabilities by dividing by probabilities. So I have to be careful. Okay. Some properties, some of it will show up in the homework. Homogeneous. You can understand the meaning of stationary. But if you translate, nothing really changes. If you take the process P and P of X, which is nothing but taking every point of P and moving it by plus X. Okay, so this is a collection of Y plus X and then 5 minus 2. They should have the same distribution. So is it obvious? What did I want to show? What is the definition of P? All that I needed was that the number of points falling in a region is Poisson distributed, and disjoint region should have independent number of points. Just by translating, nothing really has changed. You should not be able to even distinguish between it. All I've taken is the same set of points. I didn't disturb their location with respect to each other. I'm just shifting everybody. So area, so the whatever property was true earlier, the same properties are going to be. So you can do if you want. So this is more interesting. You prove it after stating a theorem. So each point of P kept probability P and remove otherwise dependently. The resulting thin process what a thin process is thin density. P. What am I doing? I'm keeping every point of P with probability P. So essentially, I go to the point, flip a coin. If it turns out heads with P, I keep it, otherwise I remove it. I'm doing, and importantly, I'm doing this independently for every single point. So it's called a thin process. It's thinner compared to the new process. How do you convince? Is still a Poisson point. Density, this is slightly easier. The density is going to be lambda times P. Because 1 minus P are gone, remaining are lambda times P. But can you convince me that this is still a Poisson point possible?
The property was still there for point.
This requires a little bit of proof. You can do it from first principle. Just try to show that the number of points falling in the region is now. It is, yeah. But is there a more intuitive way of seeing this? So this is a special property of a Poisson random variable.
Since I'm independently removing everything, so
No, but this is no. So suppose It's a special property of the Poisson random variable that if you thin it, it remains Poisson. It's not true for every random variable. So it might appear that if this process was not Poisson, it still will hold. It's not true. Is the property clear? Going on. This you can prove from first principle, so we'll see at the end of the class how to prove this. And similarly, you can take union of two independently. It will still remain a Poisson. So rather than, so this is essentially I'm throwing some points. So you take phi1 and phi2. Both of them are individually Poisson processes with lambda1 and lambda2. You mix them up without doing anything. Just take the union of the two. That is a new Poisson process with lambda1 plus lambda. That's also mentioned. Here is the most important thing. It will take care of our conditioning. Not proving. If you want to prove, let me know. I'll provide the link to that. Okay. So that's P. Okay. Condition X to belong to phi. Probability of an event with respect to P, P1 X. Event E, where this process has been augmented with the point X. It's a very strong line. What has happened is this is the event I want to look at. And the phi, given that X belongs to phi. It's equivalent to essentially looking at a new process which has phi union X. That's the interesting piece. So how to prove this is it's more complicated. Not going to prove it. But the implication is kind of so. What is the implication? What can you? How can you use this?
X already belongs to P, right? So X in P union X is not P.
This is on the left hand side. Now here, this phi doesn't have an X.
We started with X belongs to P.
Yeah. So this is a process. They want to control what is the probability of an event E with respect to phi when X belongs to P. Here I'm not assuming that phi belongs to X. They're just taking. So think of this as taking a particular realization of phi, adding X to it, and then looking at the event E. That's how you should think about it. So this doesn't mean that here X is already part of it. That's one. The way to think about it is forget the probability. Any one realization of phi, you always add X to it and compute how often this E happens, and then take an expectation with respect. It's also sometimes called palm method when you take condition PALM. Palm probability. Okay, so how can we use this to compute something interesting? But otherwise it would be hard. We observe the elements of the nodes to last now.
Ask the questions like a point belongs to a cluster and
Okay. But we not even defined a graph list. All we have is set of points. That's all we have. What about the following? Let B. Yes, that's a part. That little O. With the origin. It's set B, which contains words. This all of this is B. Close. Okay. Now, what is the probability? The number of nodes of equal to B, given that let those numbers. So, whenever I say this, it will just. How should I use the theorem? The question clear? Unconditioned, I know already what it is. What is under conditioning? What is it? So what can I use the theorem to say? This is equal to probability that okay. What is this equal to?
Number of points in equals to k minus 1 in with respect to
So I can impact. So this is an expected answer. If you think about it. It's just that I can do this so easily. The question. All we are asking is what is the probability of the BSK points given that is already given that there is already one point sitting inside. The fact is that the theorem is actually telling you exactly this. You don't have to do all the hard work. But think about if I were really wanted to do this using first principles, how would I do this? Given that this event is a zero probability event. Rancho, any idea how to do this from first principle? Suppose I did not have this theorem, how would I do this? To make this meaningful, what I would do is I draw a small ball of radius epsilon around. Are you saying something, Pancho? So now, instead of saying exactly the origin belongs to P, what can I say? That region has 1 point. This region contains the origin.
Yes.
If I say that region, let's call it P. What does it mean in terms of these probabilities? Eventually, we're going to take epsilon small, but fix an epsilon for the model. How can I represent this probability in terms of A's and B's? Then I say it is nothing but probability. See, what is conditioning really mean that the origin belongs to P means a small region has 1 point. Because as epsilon shrinks, it will shrink to 0 and there will exactly be 1 point there. So for small enough epsilon or the limit epsilon goes to 0, these two better be the same.
That right side conditioning thing I am not getting. That thing implies 0 means origin belongs to pi.
Yeah. What does it mean? This
Number of points in
A is 1. As epsilon goes to 0, where does that A go to? A collapses to the origin.
Yes.
The origin belongs to phi means that area has roughly 1 point. Right. So now,
So with respect to phi, basically means that elements are belonging to phi.
not elements, the points are being distributed according to phi. That's what it
Okay.
means.
Yeah.
What is not clear? Ask again. Don't do this.
That thing I am not getting. It means
What is not clear?
with respect to PPP phi, we are putting points in set A.
They're not doing anything else. The point process been given to you. I'm looking at a set B. I'm trying to find the probability that that set B contains k points, given that the origin is part of the process given to me.
Okay.
I'm not doing anything separately. The distribution is what is being controlled by phi. So think of a particular realization you want. For that realization, you're told that the origin belongs to the realization of phi. What is the probability that the number of points belonging to B is equal to k? That is same as if I were to put a small ball around, ball means we call it a disk in 2 dimensions of radius epsilon. As epsilon shrinks, that shrinks to origin itself.
Yes.
And this conditioning is nothing but saying that there is exactly 1 point in this region A for small enough epsilon. That's all I'm saying. I'm just replacing that condition by writing the number of points equal to. Okay. So now I've got A, I've got a B. Now we can proceed further and show that this is in fact this is equal to k minus 1. Now, what extra property do you have for the 1,000 point process? That disjoint regions have independent distribution. The number of points lying there are independent. So what can I make the disjoint? We can make B intersect with, or essentially is removed from. So if A has 1 point, B without A should have how many points when B is equal to k points? Is exactly equal to k points. This same as this. And then I'll take the limit epsilon go to 0. You'll get exactly that. P of B is k minus, because A will shrink to the origin. So it will contain all of B. So this is another way of doing this from first principles. just using the properties of the Poisson point process. But the beauty of this Leibniz theorem is that you don't have to do all this. Somebody has done it ready-made. All he's saying is, think of phi as a process where you're in addition putting an extra point. Compute everything else with respect to it. And if B did not contain 0, then what would have happened? So here I assume that,
The condition has no effect.
but that's not obvious, right?
Yes.
Without this theorem, it would not be obvious. Who knows, right? Because the point that lies at O, it could skew the distribution around itself also. It's not doing it. That. So here it's telling you that you just add that origin back over here. But if the event really looked at things outside, it should not have mattered. That's what it's telling you. But in general, that is not an observation one can directly make. If the point process, I tell you that there is a special point lying here, it could affect everything else. What it's telling you doesn't. So there's something special going on, is what I want you to impress. So B containing the origin, B not containing the origin, we with different answers. If B here did not contain the origin, we could just simply decide. Because here, if you put a 0 here, it has no effect on what this property is. It's just the fact that B exactly contains, so I need to subtract 1 out. So this is a profound fact, and this helps us in doing everything we're going to do. So that's why I wanted to come to this. But you don't really have to worry about your feet, even though your conditioning will define a particular graph, conditioning on the fact that I'm looking at the connected components of nodes which are located at origin. Things don't actually matter. You can do this without changing anything. There are many interesting results in the, okay, this chapter, not sure, I'll share this chapter. But here is the final one. Kind of very nice. For the marking term. So what I will do is look at every point of this field. Go ahead and put a mark, let's say cross and 0. 0 cross independently and so on. For each point of P, I'm putting a mark, a 0 or a cross, independently of everything. So what I will call it is a PM. Will be X and comma. X, comma. This is my mark process. Where am I? Mark. Oh. Okay, so. So far, this definition. Not this is not there. So this could be any label. Red, blue, green, whatever you want to do. Theorem is as follows. The following two statements are equivalent. Condition on locations. Exercise of in are independent. With distribution. What is happening is, if you're looking at this Poisson point process, I have attached a mark with respect to every single location. So either you can think of this as a location and a mark. What I'm saying is that if condition of the locations, the marks are independent across these locations, and their distribution is M. That's one way to characterize this process. Another is to just look at the Poisson point process on a higher dimension place. It is, think of it as 3 dimensions. R2 cross another dimension, it only takes values which are only marks. So this is a completely different process compared to this process. These two are actually equivalent, where the density of this process is nothing but. So probability measure is nothing but what is the mass associated with this process on a set of type, a Cartesian product, A cross B, and it splits as products. So this is our usual, the normal Poisson point process will have this. What this is interestingly doing is it's multiplying the same distribution with respect to the set B. So B is over the script M. And these two processes are equivalent. That's what the theorem says. Then it's in one place you can think of this as a single process where marks are associated. And given that the location, the condition on the location, the marks are identified. That's one process.
Condition on the location.
Location. So if I fix the location here, so y1, y2, y3. What you're saying is mark 1, so M1, probability of M1. Given by 1 on the way. Is it space? That's what this. You could make it even more restricted, saying all marks are in the past without even looking at the location. This gives you even more freedom. If provided condition on the location that is defined. Could simply say I'm just going to go there and pick probability P, like in a thin process. This something reminds you of the thin process. You can think of the mark as keeping it or removing it. Where it was everything was completely independent of everything else in there. So this is one particular specialization of this. This is saying even more that conditioned over the location should be independent. Independent even better. So that's one kind of process. Now you look at completely different process, which has nothing to do with marking nothing. It's just a process on a higher dimension, which is a Poisson process with a particular density, which is splits as the multiplication of the Poisson, the underlying Poisson process on RT, R2, and the process just
That thing, can you please just describe it for MD?
M is nothing but distance. You can call it the mass of. So probability mass of the set. That's all it is.
Of of a particular mark.
Not a particular, so this could be a set B, right?
Yes.
So suppose it takes only two values.
Hmm.
If B is both values, then it is one.
Okay.
If it takes only, let's say, +1 with probability P and -1 with probability 1 minus P, then it would be, if you put a +1 here, you get a P power. You should think of this as
So B will be containing those marks, right?
B is a subset of all possible marks.
Huh.
So I'm just counting the probability of all marks possibly belonging to B.
Okay.
This is standard. This is the total probability mass of B.
So every mark is having its own probability.
Of course,
Okay. And the sum of total is equals to 1. All those.
because that's what I said, distribution. That is automatically. So I should understand distribution.
I was thinking like cross and circular have their distribution. Like cross happens with probability P.
No, at this point I put either cross or zero. I'm putting one possible mark. I'm putting one possible mark with certain distribution. So with measure.
Hmm.
So I will say distribution, I should simply say measure. So now can you use this and tell me that the thin process is Poisson point process? When thinking of marks is nothing but keeping it or removing. So what are possible marks? There are possible two marks. -1 or +1. You can put -1 as removing it, +1 as keeping it.
Hmm.
So what is the second statement? So now what you need to utilize is the second statement. That instead of looking at marks and all on the first statement, the second statement, we should think of R2 by M. We just look at a single process on R2 by M. Where you're essentially suppressing all points where the mark was minus. So let's draw, let's see if I can draw it. Okay, so this is my R. This is my. If you like it. Whether I go up or I go, all the points, the usual process are lying here. But when new process, some of them have been moved here, some of them have been moved. So that's what this R2 union. Yes. R2 cross M process looks like. But I know if on that R2 cross M, so let's put a process here. This process itself is I can now forget about it. I can just forget about the middle process. Now this is my new process. Some points are lying above, some points are lying below. But I know it is a column point process. Okay. Now what is the density of any one type of points? Whatever what is the new process where R. That's what I want. So let's try to see the plus ones to be the ones which are retained. And probability of retaining is P. What is the density? It's a big one. Why? It's lambda mu. Y takes value with plus one or minus. 1 times P plus. This will, so let's take 0 and 1 so that we don't make a mistake. So I'm assuming y is 1 and 0. Like this. Now, when y only takes one value, essentially things will disappear. So it's much easier to write it plus 1 and 0. So y will simply be plus 1 times p, and this y will disappear as soon as I'm not allowed to take the values. So you simply get lambda mu into p. And the set you are interested in. Yes. That's what you're very interested. And this is caused off by the theorem itself. All you computed was the density. You can do this using some principles, but the theorem actually tells you that this is directly positive. So final use of what we've seen so far. So this thing I'm skipped. So Slivinet's theorem is just going to use this to. So leave it neighbor distribution there. Suppose there is a point x here. What is the distribution of the nearest neighbor in the field. So here is also the point. What is the distribution of the nearest neighbor of X? And for that, I need the conditioning that X belongs to P. But because of Slivene's theorem, I don't have to worry about it. I can essentially, Slivene's theorem, I don't have to worry about that. I can essentially see what is the void probability of the disk of radius R. Let's say the nearest neighbor distance is R, capital R. What is the probability that capital R is bigger than little r? Which event under P? Yeah, I should have really conditioned on X belongs to P, but Slivene's theorem allows me to get rid of that. So what is the event which I can control, which is equal to this? Yeah, so all this region, as long as there is no other point in this, capital R is greater than R. That's it. It will be to the minus lambda. That's it. Right. And from this, you can find all the means, moments, expectations, whatever. This is the nearest moment distribution. You find the second nearest or nearest. All right, so now limited time. We'll go back to the plan. Hopefully it will be clear why I spent so much time doing this.
How many minutes
Yeah, so tell me. Basically, I should have condition on X. Right? So how do I get rid of it? Okay. So that point doesn't matter.
But isn't that clear with the profit? First property about fees.
Stationary.
And yeah.
Stationary. Conditioning is something much more than this. Okay, so what I really want to study now is the following. So last time what we studied, we looked at a nice lattice and then percolation on whether these were on or off. So the probability P, we made the edge active or on or open, and then we said the connected component of origin and said when is it finite, when is it infinite. Now you want to define a graph over a Poisson point process. Take a Poisson point process P. We're going to define an edge between two vertices. If the distance between them is just at most r. So what I'm going to essentially do is to draw a circle around each node with radius r. If I find anybody inside there, I'm just going to connect it to an edge. And do this for every single node. So for this, be connected to this and this. Fixed R. So this guy looks connected here. And for the moment, the bidirections. This is nobody. There's nobody. So I can put that. So that they can all connect to each other. So that defines a graph. So in particular, let X, Y belong to C. X7, N, H, D. If only X plus Y belongs to bond, center at X with radius R. So this is going to be my notation for a bond. So as soon as a point belongs to a ball of radius r around x, it's connected with h. This defines a graph which goes in the product V or lambda. So lambda is the density of my underlying positive point process, and r is the connecting radius. Any comments on the graph?
You can always define small enough r so that there is no correlation at all.
Yeah. But look at there is something else going on. So if you fix a very small r, it'll keep increasing lambda. Right? Increasing lambda means shrinking the distances. So whatever small r you hold, I'll keep increasing lambda sufficiently higher so that there are sufficiently many points close to me. So you can always trade one from the other. So the first thing to notice is what is the expected number of neighbors for each point.
Lambda times pi r square.
Exactly. So can you give me a condition under which there will be no percolation? Given that whatever we have studied so far in the course.
Lambda dp is faster than anyone that answer.
No, that is too strong. We should be able to say even something better. We know something about branching processes also. When does the branching process go extinct? It has something to do with this. If you start from a particular node, how many neighbors you have on average? Lambda pi r square. But is it in? Once you count some of them, for the new guy, is it larger than that or smaller than that? Think of starting from this particular node. Count all its neighbors. When you go to their neighbor, some of these neighbors are already counted in terms of them. So the expected number of neighbors for this guy, which are new, are only going to be smaller than the previous. So can you give me an argument? Give me a number in terms of lambda pi r square. Says that there is no percolation. Showing percolation is hard, but showing no percolation. What if this is smaller than 1? Then there will be percolation. Universal result in the branching process. As long as the expected number of descendants is less than 1, there is never going to be incorrect. So same thing is applies here. It didn't really matter how I defined it. So that's why it's the beauty of the result is that it doesn't depend on the distribution. It just simply says expected. And here it expected only at most 1. Because if it is 1 at the start, it's only going to reduce. It can never increase beyond. Or rather, the expected degree is at most lambda pi r square. Never more than that. Then this itself is less than 1, there is no. So this is the straightforward answer. Point is now, how much can we improve? So for that, we will use Percolation. Hexagonal. So last time we did this. What are we doing? See if I can follow it. So rather than squares, we will use hexagons. So rather than having circles here, each face is a hexagon. And it's closed or open with probability Pm1 minus as before.
Face is close.
Face, defining a face to be open or closed. So if this is positive one. And cross it. So this is closed, closed, open, closed, open, closed. As before, each of them will be done with probability Pm1 minus. Now, what do you want to understand? Suppose this is what I'm looking at. Can I the connected component of the open faces with large enough? Same question only. And the analysis is not very different from this to this. And answer turns out that the PC of this one is also exactly one. Exactly same as here. The critical probability with which this hexagonal model percolates is exactly equal to.
But this phase percolation on hexagonal lattice is equivalent to side percolation on triangular lattice.
It could be. Yeah.
That is why it is hard. Is it? So does this have the relation with the?
So this answer is not going to translate exactly. But the answers, the equivalent, the answers are the same. But what doesn't imply that?
So this threshold is independently off.
But the threshold happens to be the same. But similar to what we did last time, you can get lower and upper bounds easily using the very similar ideas. So we're not going to really explore this. Somehow we'll connect this to this. That's the one. But if there is percolation here, then there is percolation here. And if there is no percolation here, then there is no percolation here. Now think about how to connect. We'll just use this as a black box. So think of what is an appropriate hexagon you want to draw. So hexagonal size S. We can call this size of S. Here the parameters are lambda and R. Then you would think of defining this hexagon lattice essentially S, such that you can connect the two equations. This one process defined over R2. This hexagonal lattice is also defined over R2. So it's covering exactly everything. Now you can define whatever you want to define by choosing S and the face to be open with whatever probability. Essentially is superimposed by choosing an appropriate S and define an event when is it open, depending on the particular realization of the Poisson process. So something should strike like why hexagon? That will tell you the answer out. What is so special about an hexagon? Question is, I want you to connect the bottom point process and the hexagonal lattice somehow. Because for this, I know exactly the answer, as long as I know the probability of the face being open. This will tell me for a particular choice of S, what is the probability of face being open once you make the connection. And then if it is greater than half, I'm done. So that will give me a condition on
Some
lambda.
relation between S and R.
And eventually the choice lambda, pi, and r square. That's really what it will eventually be. So think of superimposition, a hexagonal lattice of 5 threads on top of this. And then define a face to be open. So think of my hand as a layer on top, which is simply a hexagonal lattice. And you've chosen, let's say, S. How, when do you want to define a face to be open or closed?
When that face has the.
It overlaps at some point. Oh. Now what? Suppose you do that. What is the connection that you're making? Now what S you have to choose? So suppose two faces with a neighboring are both open. What does it mean in terms of their connectivity here? Here they're connected with their visible radius r. So supposing there are two nodes, one node lies here, one node lies here. Are they connected to each other in this graph? So supposing by your definition, a face is open as long as there is a point belonging there. So this face is open, this face is open. Now, what is the distance between these 2 points? That is controlled by S. But how far is it? That's why the hexagonal geometry comes to the picture. What is the maximum distance there could be between any 2 points in adjacent hexagonal faces? You don't remember anything. So give me a crude upper bound. As a function of S. Oh, let me know this. What I have is square root 13.
Yes.
Square root of 13. I think that is right. Stop. So what I'm doing is, if a point of the point that belonging to, then this space is open. And there is n. And closest. This is yes. Now the point is, even though these guys are neighbors and they're open, both of them. In the disk model, are they connected to each other is not the question. That's it. So if the side is S, the maximum distance between 2 corners, essentially these two corners, is at most square root 13S. This distance is at most square root 13. So now tell me, how should I get my answer for percolation? Now we are ready. You just have to give me conditions. This should be R. Sorry, this should be R. Not necessarily. Any R greater than square root 13. You get one more condition. What is the probability of the face being open?
Greater than this. R is greater.
See, R greater than this will imply that wherever these points are, it will be connected in the Gilbert disk model. Let's call it Gilbert's disk. Yeah. Think of the graph which you defined over here as the Gilbert's disk model. Now, at any 2 points here, that was square root 13S. But if R happens to be larger than that, then any 2 points here, as long as the face is open, they're also connected.
Yes.
Right. Now, all I have to worry about is what is the probability of face being open. And what is that? It is 1 minus the white probability.
Yes.
Is 1 minus into the minus lambda. How much is the area of hexagon of side S? It's 3 root 3 by 2. Yeah. 3 into 3. And one more property I need to exploit. When I looked at the hexagonal percolation, the faces have to be open and closed with independently of each other. So while when I'm mapping a face to be open depending on whether I find a point or not, these are independent because of the Poisson property. Disjoint sets, the number of points falling in disjoint sets are independent. So that is also being critically used here to make sure that the faces are open and closed independently of each other. This is true. Now, what should be the final answer? So I need this to be greater than half. Yeah. If this probability is greater than half, I have percolation. As long as R is greater than square root 13S. So I need 2 conditions. 1 minus minus lambda. S greater than and R greater than. This is clear what is going on. Construction is more important, not the numbers.
That wired thing, can you please explain?
What is the probability of face being open? When is the face open? As long as there is at least 1 point.
Yes.
So what is the complement? That there is nobody there.
Okay.
It is 1 minus the word probability. Okay. So the coupling is more important. I'm coupling a particular process with another process. That is more important. Numbers are okay. So this is 1/2 because I need that for my hexagonal grid to percolate. And this to make sure that any 2 points lying at any possible locations and adjacent open hexagons should be connected in the disk model. These two conditions are essentially sufficient. So eventually, if you put them together, you get lambda r square be greater than 26 divided by just putting these two equations together. There's nothing interesting going on. Some number is not very worry about. What you should worry about is what did I do to get here? So I took a Gilbert's disk model. So this model is called the Gilbert's disk model. This model is called the Gilbert's disk model. Yeah. Want to study percolation in the Gilbert's disk model? I don't know anything, so I go to a hexagon grid model for which I know exactly what the critical property is. I'm going to map a point lying here to this space being open or closed. So as long as a point, at least one point lies in a space, I'm going to declare it to be open. And choose the side in such a way that if any two adjacent hexagons are open, it also means that I have a connection between them in the disk model. That's the most important feature. If I choose S in such a way that if two adjacent hexagons are open, so it's like you're going from here to here to define, and then you're going back here to here, so that making sure that if two adjacent hexagons are open, it means that every point which is belonging to the hexagon is also connected in the disk model. So I went from here to here to define a face to be open. But I chose S in such a way that points which are mapping to adjacent faces, if they happen to be open, are also connected in this.
So if R is way greater than root in S, and
See, I want the smallest possible value. I don't want very large.
I have 2 points far apart, and my R is huge, so that in the disk model they are neighbor to each other.
Correct.
But in this hexagon model, they won't be neighbor.
But that's okay. I don't mind that. What did I do here? I just defined this to be open.
Yes.
So what is the question?
If I have 2 points very far apart, in the Gilbert's disk model, they are neighbor to each other, but
Yeah.
in this in the honeycomb mapping, they are not neighbor to each other.
But this is only giving you necessary sufficient. So it doesn't preclude. If you pick a larger R, possibly there is percolation which is not being captured, right?
Yes.
But that you can alternatively show that there is coupling of the order that if this increases, the percolation probability will be okay. That you can show separately. In fact, this is the invariant. You think about it a little bit. By invariant, I mean that pick one model, which is G or another one. Another model where it is lambda 2. Percolation properties of these two graphs are same as long as lambda 1 R is. That's what I mean by invariant. This is also the expected number of neighbors divided by 5. You can show this. If you can't show it yourself, see the argument in the book. To be able to convince yourself. It's just scaling it.
Every configuration which is percolating is not captured by the model.
No, so it's the objective of that and not really that. It's trying to figure out at least one bound for which it works out. It doesn't tell you for every possible. We can
So if